like that the first question was easy to answer. This is joint work with Juan Rodríguez Alcalá, who was at Complutense by then. Now it's at Amazon. I don't know what happened. It was nicer than my line.
I don't see Larry there. People who are participating.
They were not in the picture, they were on. The point here in this presentation is that with functional programming, laziness, and non-deterministic, you have several different choices. So I hope you are familiar with functional programming, but just in case, we have some examples here. Functional programming will be here. Heads of a list. The returns are there with the first two elements. Repeat put the element repeat itself with a recursive call and coin either 0 or 1. Then we have expressions which are at the left of the arrow. For example, heads of 0, 1, repeat 0, repeat 2, or coin, and values which are the results when you evaluate the expression. For the couple 0, 1 or 1, 0. We have functional logic programming, like with programs like Curry or Toy, which is not used anymore. And term generating systems like in our case, they are restricted, will be constructor based, they will be left linear, that is variable will repeat on the left hand side, but well, we write it anyway. So which are the semantic alternatives when mixing these ingredients? Well, from the operational perspective, we wonder when is it time to fix a value for each argument. So we have again these functions here, heads, repeat, and coin. So we have for functional logic programming, we have so-called all-time choice, where we fix the arguments on parameter passing. So for example, to have heads of repeat of coin, the parameter here is coin, so it becomes either 0 or 1, for example 0. So heads of this will be 0, 0 bottom, and you can get 0, 0. Of course, you can get 1, 1, but you cannot get 0, 1 or 1, 0. On the other hand, with term rewriting systems, parameters are fixed when they are used. So for the same expression, we repeat coin, coin, repeat coin. This will go to bottom, and then we have coin, coin, and you evaluate separately coin. So it can be 0, 0, 0, 1, 1, 0, 1, 1. And now we wonder how this works in practice. So for example, assume we have a program for defining grammars. We have alternative. If you have x, 5, y, you can get either x or y. You have picking star with repeat and concatenate, or goes to epsilon, that's 20. You have the choice for letters from A to Z, and a word will be a star. Obviously, this only makes sense under runtime choice, because with call time choice you will have AAA, BBB, CCCC, but you cannot have words with different letters. But what if now we want palindromes of even length? Then you have a palindrome is a pal out of word, and pal out is just putting x with the reverse of x. So reverse is defined. And this only makes sense under call time choice, because otherwise you can get anything, maybe a palindrome, maybe. So for example, you can get ABBA, or you can get oops, which is not a palindrome. What's the point here? That no single semantics for non-determinism is adequate for all cases. It would be nice to have, depending on your function, as semantics for other. And then, besides the operational perspective, we have the denotational perspective, where we wonder which is the domain used to instantiate the program rules. Again, the same program, and then you have functional logic programming, where variables go to values. Again, we have the same as before, and plural semantics, or functional logic programming, stand for singular semantics, and term rewriting systems are supposed to stand for plural semantics, where variable goes to sets values. So coin can be evaluated to a set, which is the set containing 0 or 1. So head goes to a set for elements, which is 0, 1, 1, 0, 0, 0, 1, 1, gives rise to 4 possible values. So as I said, full-time choice is equivalent to singular semantics. For a long time, it was thought that runtime choice was plural. But we saw that with this simple example that this is not correct, because C is a constructor. So if you have F, assume we have alternative as question mark. If you have F of C0 or C1 with C a constructor, you need first to reduce this, so you can do pattern matching, and you can get 0, 0 or 1, 1, but you cannot get 0, 1 or 1, 0. However, with plural semantics, this is a set of C0 and C1, and this is a set with two elements, 0, 1, 0, 1, where you can choose both of them for each value. So it's not correct that runtime choice is plural semantics. And something we would like to have is compositionality, where expression with the same value can be interchanged in the same context. I hope this is not the case. But this is not the case with runtime choice with the example we saw before. Okay. And it will be very desirable in a value-based language, right? Because the philosophy is, all I know about an expression is its set of values, and this is what we want with singular and plural, which are compositional. I'm not saying that runtime choice is not good for programming. I like it a lot, I use it a lot, but it's not good in all possible contexts. So we get to the point. What I want this talk is just combine singular and plural non-deterministic. In the same language, we can have functions, arguments, annotated as singular or plural. Of course, if all arguments in a function are singular, the function is singular. If all arguments in a function are plural, the function is plural. So we will annotate functions. For example, star is plural or val out is singular. And we provide a calculus that can be used for generating values for this kind of programming. Programs are transformed using these annotations here, and they are translated into a core language that can be executed. And our goal was to explore the expressive capabilities of this combination, because they are not very intuitive. You will see it's difficult sometimes to guess the values obtained from a combined expression of the kind. There is a GitHub with the prototype, you can access it. So the semantics of this language. And these rules are very tricky because they hide a lot of information. Well, in some cases, bottom is just bottom. If you don't want to be strict, you have any expression to be evaluated to bottom. So you have laziness. Variables go to variable. The composition is very standard for C being a constructor. And then here we have outer reduction, which is the tricky one. And maybe I can use the whiteboard for a moment. Because we are using things like this, or we are assuming that we have always in all our programs question mark stands for choice, and then we have this kind of question mark extended to substitutions. So it's applied to an expression E. It's like applying the substitution and making the thing. So for each parameter, we compute all possible substitution, we do the disjoint union, and then we apply all possible substitution to each element from E1 to En, as the whole substitution is applied to the right-hand side. Taking into account that the set should be singleton if the argument is singular and can be, it can contain several substitutions in plural. So the point here is that we try all possible substitution at the same time. And we call this, I didn't say it, but we call this semantics CRWL sigma pi, round sigma pi. And it is compositional. So nice. And all functions are singular, they behave as a singular semantics. If all are plural, they behave as plural, as expected, right? So I want to show you some examples which make it easier to understand. As I said, we have question mark as a predefined function that returns either the first or the second argument. We have T and FF and barcodes. We don't want it to be confounded with our counterparts in the implementation language. And then we have if true, then E goes to E. And all of them are plural because once an argument is singular, this is sticky. All become singular because they need to be evaluated before using. So this is our first example. We have some branches for a company. And for example, we have Madrid or Vigo or Badajoz in Spain. The employees from Madrid are John or Larry or whoever they are. For Vigo are whoever they are. And in this case, they are singular by default, but it doesn't matter because for ground terms, there are no differences. So if you want to evaluate the employees of branches, you get John, for example. If you ask for more solutions, you get Larry, and you can get everyone. But what if we look for two clerks? We define our function two clerks, just a search of employees in branches, and search, given one argument, returns a pair. And this is, well, maybe for you it's intuitive, but it is not for me at first, and we were implementing it. This is a set. Okay, this is a set because search is plural. So you can have a set and find all possible substitutions, so they appear here different values. So if you try to evaluate two clerks, you first get John, but then you get John, Mary. And you can get all possible combinations of two elements. Okay? This is not simple to see at first, at least for me, but this is how it works. But what if we don't want to have the same name twice? Okay, we can implement a different function and make it a little bit more complicated. Remember, search was plural here. Then we are going to build a list of different elements. And this is going to be singular. Why? Because with plural you have a set that is fixed later. So you cannot make sure that the same that different values go to different variables. So new int needs to be singular. And this is just building a list of different elements. X with nil goes to nil, and this is the constructor for lists. If it is not equal, X and Y, then construct. And this is one of the tricks, no disequality constraints, just round version of different elements. Okay, for true. And how to generate lists of different values with a plural function values. that goes to this constructor here. So it can pick different elements, but only works when they are different. So it's a combination of plural values in here and a singular function later here. Okay, so you generate a set here, and then it's fixed in the next function. We can make it more difficult, and you can define n values, n different values, where the first argument is singular and the second one is plural. Okay, this is the annotation for that. SP means first argument singular, second argument plural. Why this combination? Because you want to fix the number of elements you want to extract, but then the elements must be different, so the second argument needs to be a set. And here, define using the elements below above n clerks, which we wanted from some time before, and it uses find clerks, and n vals here, it fixes the number of elements, and just find clerks from the employees from the branches. Find clerks is singular, because we want to fix it, and given employee, we get its name. So if we want to evaluate n clerks from successor of Z, we get a list with John, Mary, and Laura, which are all different. I hope it makes sense. But the rule of thumb is singular arguments fix their values, plural arguments represent set of values, and they are all together in different function or in the same function in different arguments. Another example. So assume Ulysses has been captured and has a bag of gold that never infinite amount of gold. Okay, because we want to use it several times, so we want to be finite. He can interchange items and information with his guardians in order to obtain the key to escape. So we have here another singular plural function, which is ask, that fixes the guardian and then has a set of elements that he can interchange. For example, if he asks Circe with Trojan gold, he may get either the treasure mark or the siren secret. If he asks Calypso with siren secret, then he gets the chess code, and so on and so forth. So the point here is that you want to fix a guardian with the first argument and then offer several items with the plural argument. The next step to find the way to escape is to combine everything from the single provider. So you can have ask who, when a guardian, which is singular, and a message that can be a set, and it produces a pair. This is a constructor for pairs of the guardian and asking using this function the guardian for a message. Okay. So you are combining here in a plural argument a call to a singular plural function. And then final function, and this is a bit counterintuitive. To discover how to get out, you can give what you have and do a step with whatever you have and keeping with the second key what you have. So this is the, so to speak, recursive call, which performs a step and at the same time keeps whatever you have. So this is the idea. Return what I have and interchange and iterate the process, where the last key allows to use items several times. So you can ask our tool how to escape, and it says, well, first you need to use the Trojan gold. You keep asking, give me more information. Then you can use this Trojan gold with Circe to obtain the treasure map. Tell me more. You can use with Circe. You can obtain the siren secret more and more until you obtain the key from Polyphemus. So it gives you the path to the escape, asking for more with this function we saw before. So it's a way to perform deduction in this singular plural semantics. And this is implemented. And you know I can tell you that neither runtime can simulate call time nor vice versa. But it's easy just to simulate them. Runtime simulates plural very easily, just postponing pattern matching. You have this function here where this is plural, then you can introduce a fresh variable, y, and say that if the matching holds, then you do the projection of the new argument, the new variable. Where this match function and this project function needs to be defined per each function, per each argument. So we have several match functions and several project functions. And for simulate random choice, or simulate call time choice, in random choice, we need a let expression. You can imagine. The idea is that the let expression fixes the value of the new variable, then it is used in all places. So for example, let x equal to 0 question mark 1 in x forces this to be evaluated first, then bound to the variable, and then using the substitution. And we have used mod, a high-level language and high-performance system that is based in rewriting logic to implement this. What's the point for using mod? Well, mod is runtime choice, and it is reflective. The rewriting logic is reflective, so mod has a meta program, a meta level that allows you to reason about modules and to define strategies and to modify the program. So our program transformation, its execution, and user interaction are implemented in itself. We are almost done. Perfect. So what we have a formal framework that allows the combination of singular and plural non-determinism, which is a safe extension of both options and preserves compositionality. We have explored the expressive capabilities. We have several examples, but we would like to have more because it is still not easy to use, at least for us. And well, we have shown that previous mixers employed runtime choice that are different from plural. We have some extensions to do. Some I like them, some Juan likes them. For example, we would like to add higher order capabilities because we are using several functions that are defined in several places as predefined. We are kind of take, kind of fold, this kind of function that they are always predefined in other languages. And I would like very much to see how matching modulo works. Matching modulo commutativity or associativity is very widely used in mod, and they define equivalences classes for this action, which uses very much the definition of sets. For example, our question mark function should be commutative because A question mark B goes either to A and B, so this is a clear use of commutativity. And then we want to understand programs better, understand the equivalence of annotations, and study some equational laws for non-determinism. And one drawback of our implementation is that it is quite slow. We used a narrowing implementation called natural narrowing, which is very efficient, but even in using that, is quite slow. So we would like to study some kind of sharing of set of values to improve efficiency. And that's all. Try it and tell me what you think. Thank you very much.
Is your language lazy or strict?
Lazy.
Okay, so then even the call time semantics, or actually this is a question, when you have call time semantics, it is activated when you actually use the argument, or do you branch at the point where you actually call the function?
We postpone the inner part. This is the point of the natural narrowing I just said. It works like Haskell. It just generates as far.
Okay, let's say this in another way. I have a function which takes x and returns 1. X is not just a all. Then I call this function to something that has two possible values. Am I going to get 1 twice or only once?
Once.
Okay. You also mentioned that it's slow, but is this because when you have this runtime choice, you just have exponentially many possibilities, and then even if you do sharing, you still have exponentially many.
It's for several reasons. It's also because we are not computing at the object level, but at the meta level, where we are implementing by hand the strategies to do everything. So it's like the code is so manipulated that it doesn't run smoothly. I think we need to improve that. Mode includes strategies. When we implemented that, they did not exist. And maybe with that, it would be faster because it's implemented directly in mode, not at the
I did something similar in Haskell, and I have no problems with performance.
This is too slow. Not minutes, but several seconds to compute its solution with the last example. So you need to wait for this. Yeah. In our case, you need to wait, and it is not nice.
Questions? Let's thank the speaker. So, I guess we don't need to stop the recording.
Yes, I actually presented something which is not using Zoom mechanism. And it's full time. It's a question I just put in some. Remove from time. It works in a very small way.
Go back to the